Thank you. So I'm going to talk a little bit about the Unwinder, with which I mean the thing that implements C++ exception handling in libgcc and libc C++, and pthread cancellation handling for glibc. I'm mostly focused on dwarf unwinding stuff because that is the predominant unwinding format in the GNU toolchain, but I'm not going into these deep details. So why I'm bringing this up? The current state of the Unwinder is it's not async-signal-safe, which means that you cannot write a C++ signal handler which throws an exception and handles it locally in the signal handler without ever leaking it out of the signal handler. And that's actually not required by C++, but it would be nice to support it so that you can call basically any async, that throwing exceptions doesn't make functions async-signal-safe by itself. While POSIX doesn't really talk about unwinding, but it's implied by the way you have to do cancellation handling. There's some sort of exception handling construct there as well. And it's kind of iffy whether that has to be async-signal-safe in glibc in the implementation. We currently assume that it's async-signal-safe, but the implementation is actually not, and that's sort of a problem. And the current state of the Unwinder is also that it has very bad multi-threading performance, and I'm going to talk about this a little bit later. So my goals is are these. I want to find a way to support exceptions in C++ signal handlers, as long as the exception is called locally and doesn't leak out of the signal handler, because that is in general not supportable for asynchronously delivered exceptions. And the reason for that is for a future C++ POSIX interface, if it ever happens, you need to be able to call async-signal-safe functions for use in a signal handler. Otherwise, you can't write a signal handler. And if we don't have a async-signal-safe throw in C++, then you need to duplicate all these function interfaces, and that's just not friendly to programmers. And the other goal I have is I like to see better Unwinder performance. So there's currently some talk in SG14, I think, on the C++ side about revamping how they do exception handling by using a different mechanism. I think it's also called zero cost. Our exception handling is also called zero cost. So, but zero cost refers, in our case, it refers to the non-exceptional execution path, where you don't have any instructions for checking for the presence of an exception. And when you enter a function, you don't have to call register functions in the runtime library to register destructors on the stack or something like that. We don't have that, and hence we consider our implementation zero cost. But obviously it's not, but it's zero cost in the non-error case. And some secondary goal is maybe we can talk about a little bit about this, is a smarter handling of backtraces with symbols to make it safer if you have a deal close in between and you unmap part of your process image, and you want to add symbols afterwards, how you can still make that reliable in the sense that it doesn't crash. So maybe we can come up with more goals during the discussion. I hope that the slides will start something in this direction. So I want to look briefly at how the Unwinder is structured in a very high-level view. So for throwing in an exception, you have to do something on the language level to allocate the exception object and put in all the stuff the language needs. So for C++, that is the dynamic type and the user payload. For other languages, it might be less information. Languages like C, we use that for pthread unwinding of cancellation unwinding. There's only one type, so there's no dynamic type information. Ada has also only one type effectively for exceptions, so there's also no dynamic type information, so it's a bit simpler. And then the Unwinder, for each stack frame, it has to locate the appropriate dwarf program, which describes how the stack frame layout looks like at the point of the exception, and then use that dwarf program to restore the register file and move upwards in the stack. And if there's a language-specific personality routine that describes specific actions on the stack frame, then it has to call that, and then the whole thing repeats until the exception is consumed or you run out of handlers for that. There's some complications there, but that's about it. So the first issue when we talk about async signal safety is that for C++ exceptions, in our implementation at least, we allocate memory. In the worst case, I think we might even hit malloc. And that's not async signal safe. And that's kind of difficult to fix because C++ exception objects aren't fixed size, because the user can define their own exception objects, and you can deal open new object files which contain larger classes that could be thrown by the implementation at one point. So there's some talk about using movable throw-by-value exceptions to avoid that kind of overhead. But I think even if we don't get explicit language support for that, we can use an async signal-safe allocator in this case to cover this aspect, and at least for very specific exception types, make sure that we have a fully async signal-safe implementation at this point. I'm not too worried about this. There's obviously some overhead due to the allocation, and you also have the nasty property that if you allocate, the allocation itself can fail. But this is something that seems to be fairly tractable.
Does the language have, in a C++, is there a mechanism for okay. Is there a mechanism for catching the fact that the allocation of the exception failed? Or is this something just like TLS and C and C++?
I think the expectation is that the implementation throws a prefabricated standard VAD alloc object that always exists in a certain sense.
Okay, so if you run out of memory, regardless of the size of the object you have to throw, the standard pretty much expects the bad alloc to be thrown.
Yeah, and even
subsequently.
if standard can't exception can't allocate because its implementation has to allocate, then it's supposed to return a reference to a pre-existing standard bad alloc object or something like that. So that is actually covered, but you lose information this way. So you might want to know why your allocation failed. When you get the default standard bad alloc object, it might not tell you.
That's right. Yeah. Okay.
What's going on there. So locating the dwarf program, that's actually why I'm looking at this, because this is where the interaction between the Unwinder and glibc happens. So what happens there is the Unwinder in libgcc calls into glibc and invokes a function that iterates over all loaded objects and invokes a callback function that is provided by libgcc. And while libgcc has a global cache inside its callback function that is used to speed up the iteration and terminate it earlier if the object or the position of the address is known and the object is also known in the cache, then you don't have to iterate over the entire object list of the executable, but this is still a huge performance problem in a multi-threaded environment because currently the function in glibc allocates a global mutex. And even if you have just a very few exceptions, but the process is large and you end up having concurrent calls into the Unwinder, then you will see that in profiles. It's extremely bad if people abuse exceptions for control flow, which sometimes happens, but it means that this programming construct is basically unusable in multi-threaded programs. So I want to postpone this a little bit because I want to go through the entire Unwinder thing before going into too much detail here. So what surprised me is that executing the dwarf program and other bookkeeping work in the Unwinder actually shows up very high in profiles. That is what I didn't expect. So
really, have you ever really seen that? So have you really ever seen that in practice?
I faked out the log stuff in the Unwinder, and there are a couple of memset calls for large objects.
Okay, so only if you fix the mutex problem, then this shows up.
This shows up in single-threaded case even today. So it's sort of mitigated by the locking overhead, but that is kind of small. It's just the atomic instruction. But there are large memset and struct copies. There's some population count computation in there for some reason that shows up in profiles a little bit. We could eliminate that with target clones on x86 at least. The dwarf number decoding could be vectorized. That's a bit like UTF-8 decoding that we could do something there, and maybe apply some VM optimization techniques to get a faster dwarf interpreter. But what surprised me was the large memset and struct copies. It's the unwind context, which is copied in a couple of places, and maybe it's possible to avoid that with a little bit coding.
So what is large there?
Oh, I think it depends on the architecture, but on x86, I think that it's copying 2K per spec frame or something like that. So it's and x86 is not too bad in this area because we don't preserve the vector registers during unwinding. So it's actually a small register file. I don't know why. I haven't looked into details why this happens, but it shows up in profiles. So I faked the whole thing. I took out the lock in the DL iterate PH header and run that on a reasonably current CPU, I think. And what I saw was about 1,200 nanoseconds per frame with a destructor that does nothing, and probably something around 280 nanoseconds per frame if there is just something you have to unwind through, but it doesn't have any personality routine attached with it. So there's no user code that runs when the unwinder proceeds through the stack frame. And there's also a substantial startup overhead around more than 1,000 nanoseconds, I think. That was a sort of non-scientific benchmark, so just to get a feel where the time is spent there. And where I cheat a little bit is I didn't do anything about using multiple object files, multiple DSOs, because then the DL iterate p header gives you very misleading information, because the iteration through the DSO list will dominate, and that's obviously not fair in terms of to the current implementation. And so that leaves us with around 4,000 nanoseconds for a typical exception. And it's going to be much less if you just call a function and immediately catch the exception in the caller, but it's still over 1,000 nanoseconds. That sounds still bad for my original goal of saying, okay, we want to avoid duplicating C++ syscall functions. But a system call already takes 400 nanoseconds, so it's not too far away from the overhead. So if you call into the system kernel and you get back the error, then if we apply some of the optimizations, then we hopefully can bring it to a level that the exception handling overhead is not too far away from the system call overhead itself. So the idea there is that there's not enough incentive to come up with the different function calling conventions for the exceptionless case and the exception throwing case, so that you don't have two functions for everything. So what surprised me is that the binary search for the concrete frame, what's it called, frame data?
Descriptor.
Yeah,
Frame descriptor entry.
Frame descriptor entry, thank you. The binary search does not show up high in profiles, even if I have 100,000 functions in the main program. That surprised me. Maybe it's because I'm also checking the warm cache case here. I'm not checking the cold cache case, because that happens only rarely, I would say, and then the performance is probably not important for the C++ POSIX interface. Because the idea there is we want to avoid the overhead shouldn't be too large if you call a system kernel function that is expected to fail in many cases. And my idea is that in this case, then you have warm caches, and it shouldn't be the overhead shouldn't be too large. But it surprised me that even if you bump the number of FDEs to a fairly substantial count, then it still doesn't matter for the locating the frame descriptor entry. So what can we do about fixing DL iterate p header? So the global mutex we currently have in there has the consequence that we have very bad multithreading performance, not surprisingly. Everything is serialized, and it's also not async-signal-safe. And on the libgcc side, we only have an 8-entry cache for the DSOs. So if you run out of the 8, if you have a larger number of DSOs in your process and you touch everything during the unwind process, then something gets evicted from the cache, and you may have to do a full iteration the next time DL iterate p header is called. So you can have very bad performance in case of programs that load many objects, either directly during program start or later during DL open. And that is something that's tied to the way this whole thing is currently implemented. And of course, the LRU updates for the internal cache, they cause further cache line bounces. So even though it's synchronized on the mutex, you have another source of overhead there. So what we can do apply a quick fix, sort of, in glibc. So the quick fix would look like this. We still need synchronization in DL iterate p-header because DL close and DL open change the list of loaded symbols. So we need to do something to avoid data races there. But we could use a scalable read-write lock in DL iterate p-header and use acquire the read lock there, and in the DL open and DL close functions, we acquire the corresponding write lock. But we also need to change libgcc at that point, because the libgcc Unwinder relies on the lock in glibc to protect its internal cache data structures. So if we take out the lock in glibc, then hell breaks loose, because we have data races in the Unwinder. So what I did for my sort of quick fix is I took the LRU cache and made it thread local. That results in the performance numbers I quoted before. And it basically, the 40 thread case and the single thread case are pretty much identical. So it scales quite well, I think, in this department. So the question is whether the quick fix is good enough. So it's still not async-signal-safe because of the read-write log interface. It could be better that we could do something to avoid the deadlock in case of DL open, DL closed, but it's going to be iffy. Performance with many DSOs is unchanged because we didn't change the LRU cache or the way the iteration works. If we want a larger cache, then it's going to be in TLS data, so it's increasing the per thread overhead for each increase in the DSO cache size, we get some TLS data usage. And we need to introduce new ABIs because we can't drop the locking in DL iterate p-header or relax it to a read-write lock, because like libgcc, there might be other consumers of that function that rely on the current global lock. So the question is, is it worth doing this? And I'm leaning to saying no. So for the not so quick fix, this is a new interface in glibc, which basically gives you, you go in with an address, which is a program counter of some sorts, and then glibc gives you the PT GNU EH frame segment of the object file for that address. Basically uses pre-computed information, and how we implement that internally is up to glibc at that point. And this function replaces everything in the callback function that libgcc uses up until the first read encoded value with base call, which is something related to parsing dwarf relocation data, something like that. So that's the point where libgcc starts looking at the dwarf data to locate the frame descriptor entry. And It's basically right before the binary search for the frame descriptor entry. We don't have a lock anymore when we do the binary search there, and that works. We discussed that on the GCC list a few weeks ago. This works because even if you do a concurrent deal close, you can't do that if there are still objects. If the stack is still active in a running thread. So, for example, in the x86 case, we actually read from the code segment to find signal handlers and detect whether a signal handler is being exited during the unwinding process. And if you do an unmap, it's going to fall over, because we can't do that kind of operation outside the lock. That happens when the callback has returned. So it should be okay to do this kind of thing without any locks outside glibc itself. The advantage of structuring things this way is that we can do several different things to implement this on the glibc side. We obviously still have to synchronize with deal open and deal close, but how we do that is up to the internal implementation. And I spoke to Torvald about this, Torvald Riegel, who implemented the libitm stuff in GCC, I think, and is very active on parallelism and concurrency matters. And he suggested something about something based on software transactional memory concepts, where readers do not block a single writer. So a writer would be a deal close call or a deal open call. And we can achieve signal safety by keeping 2 copies of the data. The data is very small. It's like 20, 40 byte, not 20. Yeah, let's say 8, 9 machine words per loaded object. So in comparison to the overhead of doing a deal open or mapping a shared object, it's not really that much, so we can duplicate it. And 1 copy is always usable, so even if you get a signal during a deal open, you can still do the unwinding. We also could pre-compute more information if we wanted. So basically go further down in the current unwinder implementation and move more of that into glibc. And that raises the question if it may make sense to move the dynamic linker as the unwinder as a whole into the dynamic linker and into glibc. Because that would also avoid the issue of new ABIs, because the dynamic linker can just interpose its own implementation for the libgcc unwinder doing dynamic linking. So it's basically something you could backport and have in a distribution once it's upstream. And you don't have to go through the extensive multi-year process of introducing a new ABI. So that's something to consider.
So I'm wondering sort of why this particular point sort of would be the ideal point to make the interface between glibc and libgcc if you have an interface. I would have thought that a more natural point would be something like a DLP header find. We give it an address and you get back a p header pointer. And everything else is then done in the unwinder as it is today, because you don't need any locks there, and it should be just.
So, yeah. There seems to be some we basically you're suggesting we should pre-compute less information than.
Yes.
Yeah. I think on i386 you need to pass the dynamic segment to get some of the so let me go back here. The 2 entries, text base and database, and in order to get them, you need to iterate through the dynamic segment. There's something odd going on there, and yeah. So that's the reason why I thought let's put that stuff into.
So what I was thinking about is that because this is very specific to dwarf exceptions. This is very specific to dwarf exceptions already, and I mean there are today things like ARM with its own exception stuff and whatnot. So
yeah, I think for ARM you could just put in. I mean that's why I made it a void pointer and it doesn't say anything about the format as such. ARM you would have the special case and say okay, it actually gives you a different.
Yeah, well, but it's not GNU EH frame. It's something.
Yeah, it's something else. Yeah. It's worth considering. I mean, yeah, you're right. We could pre-compute less information there, and it would actually simplify the job in glibc because then the.
Because I mean, if I remember the current interface correctly, if you do an iterate p-header, you get p-header pointers, and you can do everything today starting from a p-header pointer. So, if instead of iterating over, you would just get the one that you want. Everything from there should be just the same as it is today.
Yeah, so the risk is that someone decides to add functionality in terms of additional program header segments, because you can have a large number of them, and then you get trouble with the iteration in terms of overhead. But yeah, you're right. For the current for most of the binaries you have today, it should be okay. To deal with this and make the handover point the ph header, the program header pointer, and maybe the dynamic and return the dynamic segment as well. Well, you could iterate through the p header and find that on your own too.
Oh, because you want both. Yeah, well, you could do the.
Yeah, you interpret the p header anyway. So
yeah, could find it as.
Basically, the whole mapping of the DSO is described in the p headers, right? So you can do all that information that you have in that structure. You can compute from the p header, right?
Yeah, you need the link map, but because you need the base address for.
Yeah, you need the link map, but only because the p header is not relocated. If it isn't, actually, I think it should be relocated so that the addresses in the p header that in memory should describe the concrete addresses where the object is sitting, right?
Yeah, but I think the dwarf data isn't relocated, so you need the.
What?
You need to relocate not just one pointer, but all the dwarf structure that is being pointed to.
Yes, right. Yeah, okay, yeah, so you're right. You need the base address. Sorry, yes, you need it. Yeah.
But I think for I put that in for I386. There was some very strange stuff in the Unwinder there, and there was a reason. So I sort of forgot why I did that. But yeah, you're right. We could pre-compute less. Would also make the interface more stable in the future. That's true. So yeah, that's it for me basically. I can talk a little bit more about the upcoming new function call ABI that the C++ people are working on, if there's interest, and which motivates, which got me into this. And if I work on this, I probably need help with 32-bit ARM because it's special.
So you were talking about the async-signal safety of the Unwinder, but if you want to make C++ exceptions work from signal handler, then you would need more than that, because you want to run the right destructors, even if at a random instruction get interrupted. Is that something that can work?
So we need to. There are basically 3 cases here. There's the case where you have a synchronously delivered signal and you throw from the handler. That's called, I think it's called non-call exceptions in GCC. and the Java front end uses that. I think Go uses it as well, and Ada uses it. So it's used for things like divide by 0 and null pointer dereferences. And that requires unwind data for such instructions, obviously. And then the unwinder can go, can unwind through the signal and do its job. But that's not an asynchronous exception. So it's a synchronous exception at a non-called instruction. The other case, the second case is an asynchronous exception, a signal that results in an exception being thrown. And that could be a sick child because a subprocess terminated, for instance. And that gets delivered to basically a random thread. You can't predict which thread. If you don't set per thread signal mask, then it can be delivered to any thread in the process. And that can interrupt any computation whatsoever at any point, unless, again, the signal mask is blocked. And obviously, that's currently not going to work because, as you said, you don't know where you are in the program and where the unwinding happens and stuff like that. So what I meant with asynchronous signal handlers and exceptions that are caught locally is that the signal handler itself calls a function that throws an exception, but the signal handler has a handler for that exception, so that the exception never escapes the signal handler. And I think I think we could technically support this if you want. We can still unwind all the way down, but we can't call destructors all the way down. And this is also the reason why p-thread cancellation handling is currently a bit in an iffy state in glibc, because you can cancel a thread that's running a signal handler. And at that point, you start unwinding through an asynchronous signal handler in the worst case, and then bad things happen. So that is something we need to fix.
Why does it need to be fixed?
Yeah, I think it needs to be fixed.
So I think the point that was raised in the discussions with the Austin group and other developers is that if you call a cancelable function a signal handler, and basically the cancellation of the signal handler turns what would otherwise have been a non-asynchronous cancellation into an asynchronous cancellation, and you just need to be aware of that. That if you have cancellation that might be called upon you, you cannot call cancelable functions in the signal handler, or you could get in trouble. It's kind of an educational awareness issue in my mind that you shouldn't do those things.
Yeah, but
pardon?
How do you debug this kind of problem?
How do you debug the kind of problem? Well,
I think so.
Yeah.
So my answer to that is,
yeah.
I think we can't fix that on our own just by sprinkling magic dust in the toolchain. But I think we can give programmers the appropriate tools to deal with the situation, and that might involve fixing the unwinder not to do stupid things in this case. Because we need to run the unwinder to detect this case. And then we can apply countermeasures. And if the unwinder itself is not async-signal-safe, then,
Yeah, if the unwinder ends up being async-signal-safe, then we may have a way to detect this case and basically...
just the quality of implementation issue, I think. I think the C++ case is stronger, in my opinion. So I think there is a question.
I just wanted to comment that for GCC Go, we could really use the ability to unwind a different coroutine that's asleep to be able to unwind its own stack. And the libgcc Unwinder has the data structures necessary, but they're not exported. So I'm going to comment that Cherry, who works at Google, is going to likely send in a set of patches to make that possible.
Okay. So that would, I wanted, that would sort of argue against integrating the Unwinder into the glibc dynamic linker, because then you don't profit from improvements inside glibc.
Well, I'm not sure it matters much. It would just mean that that integration would have to happen in glibc. I mean, I think it would be, personally, I have to say, I think it would be simpler all around to not integrate the Unwinder into glibc, because GCC and glibc obviously have different release cycles. So, you know, you're kind of relying on the Unwinder ABI being extremely stable, which it mostly is. But if there's any changes, it's going to get extremely awkward.
Yeah, but I think the data structures inside the object are part of the ABI. So I'm not talking about the personality routine here, but the dwarf data, you can't change that without.
Yeah, but it's not just, right, I agree you can't change the data structures, but, you know, right now we're calling a series of code generated by the compiler is calling a series of unwind functions whenever it hits an exception. And right now we know those unwind functions are in libgcc, so we don't have, there's no ABI issues. We know we're always generating code that's calling the same or later version of libgcc, and we're always backward compatible. So it's a little more complicated if we're calling into glibc, because we might be running with some very old version of glibc.
Yeah, you would still need to ship the implementation for supporting old glibc.
Yeah, that sounds a lot harder.
Installations, yeah. Yeah, there would be code duplication for a long time, that's true. That's an argument against
it. Actually, I would argue for moving the code which we currently rely on from glibc into libgcc. So actually the elf iteration, basically, moving it into libgcc, so that we are completely decoupled from glibc.
I don't think that's advisable, because the elf iteration relies on internal data structures of the dynamic linker. And we
well, actually what I just thought about would be callbacks for DL open and DL close, so on DL open, on DL close, right? And that could be registered by GCC, and that could then track all the loads and closes with appropriate data, and then just build its own data structure within libgcc, and then not henceforth rely anymore on glibc doing anything special. Right? Because I'm also thinking about the problem, well, when we move everything into glibc, then suddenly our whole unwinding mechanism relies on glibc, which is, of course, nice from a GNU project perspective, but that would rule out all other libcs, right? And that's, I don't think that makes sense from a GCC perspective.
Yeah, it depends how much code is left once you remove the support for the other architectures.
If the other libcs don't implement DL open or DL close, or then as well, there are other requirements that may make their implementations even simpler. So then again, GCC would have to have common case code for all the libcs, supporting all their semantics.
Of course.
And so it becomes a superset of the semantic support of all supported libcs. Whereas if you funnel it out to each independent libc, you might get much simpler code in GCC, which just needs to talk to the respective interfaces that implement DL open, DL close.
Yeah, but the complicated code then is in the libcs, so it's just moving. I don't think that's arguing for or against.
So the problem I have with the DL open and DL close callbacks is that from a locking perspective, and which locks are held at that point, and what you can do another DL open and stuff like that, that's going to be quite difficult.
Yeah, but that's just a documentation thing, right? The callback can't do a DL open itself. Inside the on DL open callback, doing a DL open.
Yeah, people do that from elf constructors. So.
Yes, I know, but
yeah.
that it's just would be a requirement, right?
I really don't like the callback interfaces, but yeah, if you provide a link map at that point and everything basically to pass the in memory.
Well, in any case, I only wanted to argue for having as few code in glibc for supporting unwinding in comparison to having as much code as possible in glibc. Basically, I want to leave it staying on the GCC side.
Mm-hmm.
So the reason we have very different unwinding support in ARM32-bit is that in the embedded market, code size is still important. And by that I mean the code and the associated runtime data. And it's just, even today, it's pretty expensive to use basic synchronous unwind tables in the dwarf style. So if we're going to go to something that requires non-call exceptions and fully asynchronous exceptions, we've got to find a better data structure than dwarf for handling this. It's just too expensive.
Okay, but that's the. I mean, you are not affected by this because you already have your own exception handling.
Well, we do, but it only handles fully synchronous exceptions.
Yeah, but as if you throw in a single handler, then from the Unwinder point of view,
then we can't support it. End of at present.
Well, the format could have been asynchronous, but it'd be pretty inefficient to do so.
The point is to take asynchronous exceptions. You've got to be able to unwind from any point in the program, and that means that your entire program has got to be built
An awful lot bigger tables.
in each huge tables, and dwarf is just not efficient for this stuff.
No, it's the ARM format.
Sorry.
Once you have separate bits of tables, a separate structure.
I think the confusion is we are in an async single context, but from the Unwinder perspective, you get, when the Unwinder is called and you catch the exception before it leaks out of the async single context, then the only thing you see is call address exceptions. You only unwind through the part of the stack that has basically a synchronous unwinding path. So you should be good with your current implementation there.
You would have to stop at the asynchronous signal boundary.
Yes.
Yes.
Yeah, that's the case he was talking about. Basically, it doesn't leave the single handler.
Because that's the interesting case for, I mean, you can't really write a generic async signal handler that throws an exception. What is that going to do to anything that the signal handler has interrupted? That's not going to work.
Part of the point is that when C++, when you get out to the point where, so we work with the Austin group, we work with POSIX, we try to keep pushing the standardization of a number of functions. When you get to adding C++ kind of like things in the future, like Florian said, you don't want to duplicate those functions. So you still want to be able to, in the handler, call a POSIX function that might be C++, a C++ function, be able to catch its exception, and then do something, and then maybe terminate. But you're never going to throw back again. So
as long as you're not throwing back into the
correct.
main program,
That's why I think
the
ARM format for exception handling should work just fine, because from its perspective, it's as if I'm here and I called and then I threw, and now you have to stop there, right? There's no.
And if you don't catch it, you get a terminate at that point.
Yeah, undefined behavior. Eat your babies. So, I mean, my question for you, Florian, is what's next? Like, what would be next? I think there's maybe some there's some discussion of how much goes into GCC, how much goes into glibc. It seems that the current split between the two seems about right. What might be next here?
I think, from my perspective, would be interesting to get feedback if you want to change anything here at all, or if we are currently happy with things how they are. And well, what we need to discuss on mailing lists is whether we go into the direction of DL open, DL close hooks, or this new function interface, or moving the Unwinder into glibc. So that's something we probably need to decide very early on.
Yeah.
So and then settle the matter of how much we want to pre-compute if we use an interface like the deal EH frame info.
I mean, so there's a question from David. Oh, sorry.
Yeah, I just wanted to, or more comment, remind, I mean, that, like AIX. I mean, like not every system is ELF. Not every system, I mean, it now has, you know, it has dwarf support for exception handling, but GCC has always provided its own self-consistent internal exception handling, and it's you're at least making an assumption here or an assertion about what GCC and G++ are going to do if you're now going to say that the system exception handler has to be able to support whatever this, you know, exception handling that the language, the compiler implementation is going to do. I mean, that's a new requirement on the system.
No, we can't. I wouldn't put that as a requirement for the system because we obviously need to be compatible with older.
Right, and at that point it doesn't make sense to have it in glibc because GCC needs, for instance, a found copy of the dwarf interpreter anyway. So
it depends on the code complexity that results from the split. I would.
Yeah, well, if you want to have an unwinder in the dynamic linker, then it needs to have a dwarf interpreter. And you need it on libgcc as well because you want to support libcs that don't have it. So now you have two copies. Now we do an extension for new dwarf opcodes for better encoding of our dwarf tables, and we implement that extension in libgcc, of course. And then we also need to do that in glibc. I don't think that makes much sense.
Yeah.
But I wanted actually to comment that, yes, the multi-threaded performance problem needs to be solved. So, no, we are not fine with the current state. I just wanted to say that.
Might be a good time to wrap it up.
I can talk briefly about. It stopped. Okay.